1. Hi everyone, and welcome to the Module 7 lecture guide. In this lecture guide video, we're going to be going over the two main ideas in this section, which are the significance level and the confidence interval. So the significance level, we'll start there, is something we've already seen before. It's something I've told you what the number is for this, and we've just gone with it. So up to this point, whenever we've done a hypothesis test, at the end of it, you did something like, here's my p-value, okay, well what do I do with this p-value? You've looked on our little table or little number line and you've said, all right, is my p-value bigger than 0.05 or less than 0.05? And based on that, you made a conclusion. Well, I just told you that this 5% or 0.05 is the cutoff we're going to use, and we didn't talk any more about it. Well, that number that we use as our cutoff is called the significance level. So the significance level is the cutoff you want to put between null plausible and evidence for the alternative. All right, so what we're going to do going forward is we are going to change that number, possibly. Sometimes it'll be 0.05, sometimes it'll be smaller, 0.01, sometimes it'll be bigger, 0.1. And because now we are able to change that number, we need a name for it. So all we're doing with this significance level is we're giving a name to something we've already seen, and we're allowing ourselves to change it. Okay, so we can see a little picture of this, what it looks like to change. So we go down here. So previously, we have looked at this picture. Our cutoff was 0.05, and so remember, this red piece from 0 to 0.05 was, ooh, that's really small. Let's say evidence against the null. Okay, so let's throw out the null if we're in this red. All right, but what if you're not? If you're in this purple, you're bigger, greater than 0.05. We'll go, okay, that's big enough where, all right, the null's plausible. Let's not throw it out, it's plausible. So what's the new thing here? Why am I telling you this again? Well, the significance level is alpha equals 0.05. But I can change that. If I want, I can do a significance level of 0.01. So I'm changing the cutoff. All right? And so what does that look like on a new number line? Well, now your p-value has to fall into this much smaller range, 0 to 0.01, for me to say I'm going to throw the null out. I like the alternative. If you are bigger than that, now you're in this purple, and I'm going to say, okay, it's not small enough, the null is plausible. So just pictorially, you can see here, if I make my alpha, my significance level, my cutoff, if I make it smaller, 0.05, 0.01, if I go smaller, then I've got a smaller range here of numbers for my p-value that I can get in order to throw my null out. So I've got this much larger range of numbers here for the p-value where my null is plausible. So in essence, I'm making it more difficult to throw out the null. You've got to convince me more to throw the null out. So let's say it again. If your alpha gets smaller, then that means you need more evidence, more convincing to be able to throw out the null. So now the significance level is like a knob we can turn. And the knob, the reason we turn the knob is depending on what we're looking at, what we're studying, what problem we're trying to solve, we may need to turn the knob so that we need more evidence than in our general case to be convinced to throw out the null. And we'll talk more about this later, but the reason you should be thinking about this is a lot of the time you're doing statistical analysis, you may want to be asking a question in which, depending on your answer, you might do something. So maybe you have two options. Your null hypothesis, if that's plausible, you'll do option A. If you throw out your null and you say, nope, I've got evidence against that, you'll do option B. And so remember, using statistics, none of this is perfect. So there's always a chance you could be wrong. And so turning that knob, this alpha knob, where your cutoff is going to be, is like trying to lessen the chance you could be wrong in one of the two directions that you could mess this up. So it's all about saying, okay, I'm going to make it harder for you to convince me to throw out the null, because I want to be even more sure if I'm really going to throw this null out and go with option B. So it's all about the problem that you're considering, whether or not you want to have 0.05, 0.01, or something else as your cutoff. Right, so we'll explore this a little bit more later, but just to start, you can use these pictures to try to understand the connection between alpha and how strong the evidence, or how much stronger the evidence is for you to throw out your null. So again, I got a smaller range here, so it's even harder for me to get a p-value in that range. Okay, so that's a significance level. Where's our cutoff? Alpha 0.05, here's our cutoff, red, purple. Alpha 0.01, look at our cutoff, red, purple. Okay, so let's do an example where we can try to apply this idea of significance level, and we're going to change our significance level to 0.01 in this problem. So these problems, if I don't tell you what it is, you can assume 0.05, but if I want you to do something different, I will always say it in the problem. Use the significance level of something. So be on the lookout for that. It's never going to hide in here, right? If I want you to do something other than our 0.05 we've been doing, I will always tell you. So we want to know if a drug, a new drug, reduces the proportion of people who suffer from a certain side effect. So I've taken this and put it down here in my alternative. The new drug reduces the proportion of people who suffer from a certain side effect. Right here. The new drug is better. The proportion means pi. Immediately I see this word, I'm writing pi down. The proportion pi of people who have the side effect is less than 0.08. Why 0.08? Well, what's the next sentence say? The current drug, the one I'm comparing to, that people use, creates the side effect 8% of times. So if I want to test if my new drug is better, the alternative here, I need to look at and try to get evidence for the percentage of people who have the side effect being less than the old drug. If I have evidence that that's true, I have evidence my drug is better. Well, what's the nothing case in this? What's the not that? Well, the nothing case here would be the new drug's not better, it's the same. So there's no improvement using the new drug. All right, so pi equals 0.08. Okay, so that's our setup for this problem. Either the new drug is the same as the old and the percent of people who have this side effect or side effects is 8%, or it's better and it's less than. Okay, so at this point, Unit 1, what do we do now? Well, we run a simulation, or if we want to play with some of our new Unit 2 tools, what we can do is we could use the theory-based approach to create our distribution and try to find our standardized statistic. We're just going to do a simulation here. So down here you can see the simulation. I've told the computer, hey computer, 0.08, that's what I'm assuming. That's the nothing case, right in here. Pi is 0.08. Hey computer, we used 240 people, okay, and give me 1,000 dots. So I do that. Right down here I see, okay, here is my sample distribution. Hey, look at that. The middle is about 0.08. Who could have predicted that? Us. Okay, what else? Here's my statistic, 0.52. Well, where did I get that from? Go up to the problem. What happened to those 240 people that we had? We conduct a random sample of 240 users of the new drug and find 5.2% suffer from the side effect. So that's our statistic. So I find that on my picture. I count all the dots there and to the left. Why did I to the left? Well, because we're interested in if our new drug is better. Better would be less people have the side effect. Smaller proportion have the side effect. So I count all these dots, and the computer tells me that that's a p-value of 0.045. So I've got my p-value. What is my next step with the p-value? Always. Well, it's to figure out, does this p-value tell me null is plausible, or does it tell me, actually, I've got evidence for the alternative? So what had we done up to this point? Well, we took this number and said, is this less than or bigger than 0.05? But go back to the problem. We have a significance level of 0.01. So we throw out 0.05. I don't care about that in this problem. Compare to 0.01. So I go down here. My p-value, just reading it right off, is 0.045, or 4.5%, if you like percents better. That's bigger than 0.01. So previously, this actually would be smaller than our cutoff back in Unit 1. But now I've changed the cutoff and it's bigger. So what does that mean? It means, you know what, I can't throw or reject the null. I can't throw it out. So in that case, I have to say the null is plausible. So what does that mean in this case? Context? Well, I can go back up and I can reference this. I'm saying this is plausible. So we just have to grab this and bring it down. I'm saying this is plausible. The new drug is not better. The proportion of people getting side effects, it's plausible that it's 8%. I go down here. It is plausible the new drug does not decrease the percent or proportion of users with side effects. I do not have statistically significant evidence, in this case, that the drug is helping. Boom. You could say it all these different ways. You can reference 0.08 if you want. All good. So I changed my cutoff, and so now I fail to reject. I can't quite get there. I don't have enough. Right? Okay. So we're going to use this in confidence intervals a little bit. So just to recap what we just did, because this is important for seeing what the confidence interval is. Up to this point, our hypothesis tests, just like what we did above, have looked like this. Figure out your null hypothesis, which in the last case was pi is 0.08. You've got your p-hat, your statistic, and you've got your cutoff. Then what'd you do? Well, you used a computer or our theory-based approach. We just used a computer, but remember, we still have the theory in our pocket. We use that to create this picture, right? Our sample distribution or our null distribution. Okay, then what do? We take our statistic, we compare it, we find a p-value or standardized statistic. We could do either, right? And then we take that number and we compare it to our cutoff. In this case, again, our p-value's bigger than alpha, so null is plausible. Right? Plausible that pi is 8%. Okay. So from this work, we believe that 0.08 or 8% is plausible. It's a plausible value for the percent of people with side effects. But again, this is useful, this is helpful, but what if we want to do more than that? What if we want to find out a better idea of what values pi really could be? Because all we've done so far is, okay, 8% is plausible, but what if I want to know if it's 7% or 9% or 10% or 11% or all these in between? Well, that's where the confidence interval comes in. The confidence interval, once we calculate it, will give you a range of values that under this work we can do, this hypotheses tests, will all be plausible. And so how do we make this thing, right? So what if I want to know if these numbers are included or all the possible percentages I could want to think about are included? So we're going to do it kind of the down and dirty way. We're going to really take a little while to do this. And then in the next module, we'll look at how we can use theory to kind of quickly do this. So the theory will save us because this next process is a little long, but I think it's not too bad to think about what's happening. So it's just really used to illustrate what's happening. And the important thing is going to be, once we have it set up, can you understand the confidence interval and write out in context what's happening? So that's going to be the important thing. So let's get to it. So how do we make this confidence interval? Right? So first of all, the confidence interval is an interval, so a range of numbers, of plausible values for the population parameter. We're going to see this in two ways. Either we're going to write it as a statistic, because that's, remember, always what we start with, our statistic. Then we're going to plus or minus, go to the right and left by some margin of error. This term here should look pretty familiar to you, right? It's an election time. There's lots of polls, and if you go and you look at polls, you'll see a number thrown at you. This percent of people are going to vote this way. And then in tiny, tiny writing, you'll see something like the margin of error for this poll is something percent. That we are right there. That's the same idea for margin of error as we're going to be talking about here. Because remember, we're never perfect with statistics. So we can never give you, this is the right answer. We can at best say, this is a range of answers that we have, a confidence interval. This is a range of answers, right? And so we think maybe, it's in here somewhere, which means there's some error. And so the margin of error just describes how much error, how much range there is in the values we're giving you, because we can't be perfect, right? So how do we make this? It's right here. Right, I'm telling you this amazing thing, this set of plausible values. It's perfect. It's awesome. It's not perfect, but it's great. Right? How do I get it? Well, the way we're going to start is, well, they're plausible values. How do you tell if some value for pi in this case is plausible? Well, you run a hypothesis test, and you have to make sure your p-value is bigger than your cutoff. So how do I actually do this? I just test them all. Which sounds terrible, I know, but I'll show you what it looks like. I just test a new number, do it again, do it again, do it again. Check the p-value, check the p-value, check the p-value. And I write down plausible or nope, I threw it out each time. And by doing that process, I will have created a confidence interval. So in this example, we're going to be using the same setup, or very similar setup to the last problem, in which we have a drug that we want to know the proportion of people who suffer from a certain side effect on this drug. We're no longer comparing to the old drug specifically, because previously that gave us our one value for pi to test. But we don't want one value of pi to test. We want to test as many as we need to in order to find all the plausible values, and all the values that we don't think are plausible we want to reject. So, going back through this, we've got a sample of 240 users on the new drug and find that 5.2% of them suffer from this side effect. So 5.2% of the 240 users who we put on this drug have the side effect we're interested in studying. We're going to use a significance level of 0.05 for this. So just like in Unit 1, 0.05 is our cutoff. So, how do we construct the confidence interval? Well, we have to start testing somewhere. And the best place to start testing is right at your statistic. So what we do is we say, okay, I'm going to take my statistic, pi equals 0.052, and I'm going to run a hypothesis test with this as my assumed value. So this is a little weird that we're doing this maybe, and the result is going to be a little weird too, but if you think about it a little bit, it shouldn't be too bad. So first things first, when we do this test, we are always going to be doing two-sided tests for our confidence intervals. So we're going to test both bigger and smaller than this value. Okay. And so what we do is we put it into our simulator, and we end up with this picture here. So we end up with all the dots red. And why is that? Well, we told the computer, I want you to pretend that the true proportion of people who get the side effect is 5.2%. It did that, so guess what? The center of the picture, 5.2%. We know that that's what should happen. And then we said, okay, computer, give me the p-value. Go find my statistic, 5.2%, and count all the dots at that or more extreme. Well, that's the middle of the picture. Our statistic and parameter are actually the same number. So all the dots are either at 0.52, bigger or smaller. There's no other option. So this is a little bit of a weird one, but we actually get a p-value of 1. We almost have never seen this before. I don't think we've seen this before. But it's only because we said, computer, assume that the parameter is our statistic. So of course all the dots are going to be at or more extreme our statistic. It's right in the middle. So this is kind of a tricky one, but tries to nail home the point that our statistic is going to be at the heart of our confidence interval. So we build from the statistic. So our statistic that we get will always be in the confidence interval, and it'll be at the heart of the confidence interval. So that just reassures us of that. So here's where we get to do some more interesting stuff. So what do we do from here? Well, we take 0.52, our statistic, we write it in the table. Our p-value was 1, and based on our cutoff, 1 is much bigger than 0.05, plausible, and I've highlighted that green. Okay, then what do we do? Well, we start testing out new values for pi, so that's this column, that are both bigger and smaller. So we're going to go both directions, up and down here. Okay, so let's start with 0.047, why not? We take this, we put it into our applet for pi, we run our simulation, we find our statistic and we count the dots, and we get a p-value of 0.534. Well, that's again very big, much bigger than a cutoff, so it's plausible. So, okay, fits into our interval. Try the next one up. So we are increasing by the same fixed amount, 0.005 here. So we try the next one. This value. Do we think it could be this value? Plausible? Get a p-value. Yep, that's big. Plausible. Try the next one up. Is this plausible? P-value still big enough? Plausible. Keep going. 0.032. Now we're at 3.2% of people. Is it plausible that 3.2% of people could have this side effect? Well, this is our p-value. Still bigger than our cutoff? Plausible. Okay, let's do the next one. Now 2.7%. Is it still plausible that 2.7% of people could have this side effect? Well, actually, our p-value now is smaller than our cutoff, so nope, we throw it out, we reject it. And what you can try to think through, but I'll just tell you is true, is that once you found this reject here, all the other numbers that you're going to pick going up, so, or in this case going down, I guess, 0.027, 0.022, 0.1, all of those numbers that are smaller than this, we're going to reject them all. So once we've rejected once in some direction, we can stop. So that's an important thing. Once you have rejected a possible value for pi in one direction, you can stop there. You have your last number in your confidence interval right here, and then you go the other direction. So we are done here because we hit a reject. So remember, this was our start point. Now what do? We start making the numbers bigger, and we test. Okay, so we tested this already, plausible. We go to 0.57. Okay, we plug that in. Big p-value, plausible. Try this now. Plausible. Try this. Plausible. Plausible. Big P, plausible. Still p-value 0.62, bigger than 0.05, plausible. And then eventually, and you can see this here, we end up getting a distribution in which our statistic, 0.052, is just extreme enough to come under our cutoff. So here's our p-value. Remember, our cutoff is 0.05. This is smaller, so we're going to reject it. So 8.7% of people getting the side effect, that is not plausible to us, throw it out. And so altogether, we are left with the green values here. These values, all the percentages in this range, are plausible to us. Based on our statistic, our information, we think, okay, any of those numbers here are plausible. So we're going to write this down, but these are the numbers we want to focus on. So we take this, we go down here, and we write it as an interval. Number, comma, number. Smaller number, comma, bigger number. So our confidence interval is 0.032 to 0.082. We can rewrite this if you want, if it's easier for you to see. 3.2% to 8.2%. That's our confidence interval. We believe, to us, it's plausible based on our information, the statistic we gathered from the 240 people, that between 3.2% and 8.2% of people will have a side effect when taking this drug. And I wrote that out here. it is plausible that the proportion of people who suffer from a certain side effect on this drug is between 3.2%, 8.2%. All right? So there you go. Whew. So it's a lot of work to create that confidence interval, but again, in the next module, we'll be going over how you can do it really quickly using just technology or using a formula and our theory-based approach. So it's not going to be too bad. The key component, once we have learned these new methods to make this calculation easier, will be here. This is going to be the really big thing, is understanding how to interpret the answer you get. That's going to be number one thing we have to focus on. Okay? So the next idea is of confidence level, and this is going to be something we're going to apply to our conclusions for our confidence interval. And so it's just a reframing of this idea of the significance level. Okay, so up to this point, the significance level has just been our cutoff, right? So our cutoff here is alpha of 0.05. That was what we did in all of Unit 1, but remember this can change. Okay? Well, if we change that, we get a different confidence interval. So we'll do some examples of that. You'll see what that looks like. Okay, so what's confidence level then? Well, the confidence level describes how confident we are in our range of values. So I have a range of values I'm giving you, my confidence interval. And this range of values is supposed to represent all of the possible numbers I think are plausible for this. But so I give you that, and I also need to give you how confident I actually am in the information I'm giving you, right? Because depending on the significance level, remember, a smaller significance level, compare these two numbers, a smaller significance level, right, meant I had to be even more convinced, more sure to throw out a value for the parameter, right? In order to say, no, not plausible, I had to be even more sure. And so the confidence level just describes that to us. And the way it does it, it's really nice, is all you do is you take your significance level and you take the opposite of that. So 0.05, what's the opposite of that? Well, it's just what's left over from 1. So 0.05, 95. So 5%, 95%. So again, the opposite of our 5% cutoff here is the 95%, right? 5% of our samples are going to be, let's throw out that null. The 95%, the rest of them, and this remember goes on, the rest of them in purple, that's the 95% of samples that are, okay, plausible. All right, so we have this idea. Confidence level describes how confident you are in the answers you're giving. Right? And what we see here is that if you take your significance level, your cutoff, and you make it smaller, then what happens? You can claim to be more confident in the answer. It's taking me more evidence to throw out a null hypothesis. So what does that mean to me? It means, okay, if that's true, it takes you even more evidence to throw out the null, then I'm going to be more sure of the answer I'm giving you, because it took me even more evidence to throw an answer out. Okay? So that's the way you should kind of be thinking of this, is that it's taking me even more evidence to throw something away, so then I'm much more confident that I'm giving you the correct range. That's all that confidence level says, is it's describing how confident I am that when I give you my range, my confidence interval, the right answer is somewhere in there. And that confidence that you have changes based on the significance level. The smaller the significance level, the higher your confidence level. The more confident you are, you've got the right answer somewhere in there. So how do we apply this? Well, we apply this confidence level in our conclusion. And our general conclusion is going to look like this first line here. We are some percent confident that the population parameter, pi, mu, whatever it is in that case, lies within the, and then you put in your confidence interval. So the problem we just did, we had a cutoff of 0.05. What does that mean? It means that we are 95% confident that the proportion of people who suffer from a certain side effect, remember that was our pi, is between, and then here was our confidence interval. So we are blank % confident, throw in your parameter, is between, throw in your confidence interval. Perfect form of our conclusions. So we're going to do this. We're going to change up our confidence level for different problems, and so that's going to change how confident we are. And here's a little table of the ones that we are going to use most of the time. This middle one here, remember that's the one we've been using this whole time up to this point, 0.05. We are 95% confident in our answer at that level. If we turn the knob, remember we're turning the knob, saying nope, you have to do even more to convince me to throw out the null. I go to a 0.01 significance level. That means I'm even more confident in the answer I'm going to give you. But I could turn the knob the other way. I could say, you know what, I'll just make my significance level 0.10. I'll make it easier for you to convince me to throw out the null. Well, if you do that, then the answer you give back, you will be less confident in that answer. Okay? The easier you make it on me to convince you of something, the less confident we'll be in your actual answer. Okay. So what does it do, changing this to your confidence interval? Because we haven't really talked about that, and at this point, why wouldn't you just always do a 99% confidence level? So let's check this out. So in example 3, we're going to be looking at a random sample of 1,011 adult Americans, and they were each asked if they consume alcoholic beverages. 647 of them said that they did. We are going to create 3 confidence intervals at different confidence levels, 90, 95, and 99%. And then we're going to write out what each of those means in context and just see what we think about them, compare them, contrast them. So I have done, again, the work for you in testing out all of these different possible values for pi. So what did I do? I said, okay, let's start with the statistic, p hat. P hat is 647 successes out of 1,011 adults total, sample size. So 64% of people in my sample said they consume alcoholic beverages. Okay, so how do I make the confidence interval? Well, I start there. I test that value, 0.64, just like we did in Unit 1. This is going to be my null hypothesis, is 0.64. Okay, and I'm going to put that in. I'm going to get the p-value, get a conclusion. So let's scroll down here. Here is me putting in 0.64. I throw it in. I run the simulation, and just like last time, because my statistic and my null hypothesis were the same number, all my dots are at my statistic or more extreme. So that should hopefully make sense that your statistic is going to be a plausible value, right? What's our confidence interval? It's based on our statistic, what are plausible values for the actual true parameter? Well, the statistic is our best guess at the parameter, so that should probably be in our plausible value. So we throw that in there, start off, we are plausible. And it doesn't matter at what significance level, right? We've got all these different significance levels. It doesn't matter what significance level here, because 1 is bigger than all of these. So 1 is bigger than this, bigger than this, bigger than this, so boom, 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 plausible. Okay, so what did we do last time? We go from there. We start trying other values for pi that are bigger and smaller, and we do that until we run into something we reject, and we stop. So we see that if we choose pi to be 0.64, which was our original statistic, then we're going to get a p-value of 1 because everything is at that point or more extreme, and so that's plausible. And yeah, that's fine. Our statistic should be plausible, a plausible value. So then we start decreasing from there to test new values, or increasing to test new values. Each time we test a value, we throw it in the simulator, we look at our statistic, which remember, our statistic stays constant. It's that 0.64. We are always checking our statistic against these distributions. So that's what these 3 pictures are showing. Always 0.64, 0.64, 0.64. We're always checking 0.64 against these distributions. What's changing each time is the center of this picture. So we keep checking. Too big, too big, too big, too big, too big. Now, here's where we have to start thinking. Depending on our cutoff value, we may say too big, or we may say, okay, this is small enough. So as we go up this way, we'll start here. 0.188 is bigger than all three of our cutoffs, which are right here. So this number here is bigger than all three cutoffs, so plausible all the way. But what we see is once we hit 0.099, that is now smaller than 0.10. So once we've seen that our p-value is smaller than our cutoff, we're going to put an R for reject and stop. So these are all rejected forever and ever going this way now. So we've hit the end of the plausible values for our cutoff of 0.10. We can go one step further in the 0.05 case because this is still bigger than this. 0.099 is bigger than 0.05. But if we take one more step up, we end up getting something smaller. So we'll start rejecting, and then it's rejecting all the way. And then the last one is our largest set of plausible values, p for plausible, goes all the way until we hit a p-value of 0.009. We'll reject there. So we can see the same thing happen on the other side, right? We start at 0.64, we get bigger, 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 okay? And then for 0.10, remember that's right here, for 0.10, we reject at this value of pi, 66.5%, but we're still plausible for the other two. And then we just keep going until we hit reject in either case. So what do we do at the end of this? Well, we take all of our plausible values, and remember, I only care, in this case, about the values I picked for pi. The p-value is just a tool to help me answer the question. I'm after our possible values for pi, so I only care about reporting these numbers highlighted on the left. I don't care about having to tell you the p-values at the end, just these values. Right? And so you can see a couple of the distributions we created. For this one, 0.68, I plug that in as my pi. I have my sample size, I ran my samples, and here's my p-value. So you can see where all the pieces are coming into this table. This number is smaller than all three of my cutoffs, so it's reject across the board. So those values, so that value, 0.68, 68%, would not be plausible for any of my cutoffs. Okay. So what do we get out of this? Well, when alpha is 0.01, let's go back up. That was our first column here. Our plausible values come from these rows. So this is where p is under this column. So that's 0.605 to 0.675. Here it is again, 0.605 to 0.675. Every number in here I claim to be plausible. Okay, so I can write that in a sentence. We are 99%. Remember, that just comes from the opposite of our alpha. We are 99% confident that between 60.5% and 67.5% of adult Americans consume alcoholic beverages. All right, what about 0.05? Well, we go to the second column. What was plausible if this is our cutoff? We saw it was between 0.615 and 0.665. These are the plausible pi values. When I plugged it into the applet, I got a plausible value for the p-value. So my p-value came back bigger than my cutoff, so this is plausible. So I go back down here, and I end up with we're 95% confident that between 61.5% and 66.5% of adult Americans consume alcoholic beverages. Okay, so we can notice something here. Let's compare this one and this one. Let's compare these two. When we went from 0.01 to 0.05, we dropped confidence, right? 99% to 95. I've dropped my confidence here. And let's think about what happened. by dropping how confident I am, I can give you a smaller range of values. So look at what happens. This range of values, this confidence interval, is bigger than this one. And we can kind of see that a little bit better in the table, right? This had more plausible values than this column. So that fits the way we were thinking about this before. I can be more certain that I have found a range of answers that includes the real actual answer because I gave you more numbers to check. That's the idea. I can be more confident because I gave a little bit more room for error. I gave you a larger range of values. Right? So that's why we can be more confident, because we end up getting a larger range of values. I'm telling you it's somewhere in there. If you give me a small range and I say it's somewhere in there, well, then I'm going to be less confident that I'm actually correct. But if I give you a larger range and say, okay, yeah, this range of numbers is bigger, but I'm more confident that it's in there. So that's all that's happening with the significance level, right? The significance level and the confidence level just tell you how sure you're going to be about your answer, and the higher the confidence level, the more sure you are, the larger range you're going to have of plausible values. Which, depending on, what you're trying to do, maybe you don't want such a large range of plausible values. But if you're okay with having a larger range, then you can be much more confident about your answer. And then finally, we get to 62 to 66%, right? This is the smallest range of numbers, but that fits because we are only 90% confident about our answer here. We're 90% confident between 62 and 66% of adult Americans consume alcoholic beverages. If I want to be more confident that I've really captured the true proportion of Americans who consume alcoholic beverages, I have to give you a larger range of possible answers, which is this and this. Okay, so what we're going to do now is we're going to go into looking at an example where we are given a confidence interval, we interpret it, and then we take another step here that actually doesn't have to do with statistics, but is an important piece to the puzzle of doing statistical analysis using confidence intervals. So let's read the problem. It says, in a test of weight loss programs, 40 adults used the Atkins weight loss program. After 12 months, their mean weight loss, their average weight loss, was found to be 2.1 pounds. So of the 40 people, there was an average weight loss of 2.1 pounds, which we're going to represent as a negative number so that it's telling us they lost weight because it was off of their weight. So we're going to represent this as negative 2.1 pounds lost on average for the 40 adults. They also had a standard deviation of 4.8 pounds. So we are going to show next module how we can use the theory-based approach to this and or just a computer to calculate these confidence intervals. Although technically we could make the same confidence interval by simulating this quantitative variable here. We could simulate by taking mu to be negative 2.1. Then mu is negative 2. And then negative 1.9, negative 1.8, and just trying, and then going the other way, negative 2.2, negative 2.3. We could just continuously test these different average weight losses until we rejected a value above and below, just like we did. But we're not going to do that here. I've already done the work for you. This is what we get. This is our set of plausible values. So let's interpret this in context. We are blank percent confident. Where did that come from? Well, I told you it's a 95% confidence interval. That's it. Okay, what about the next piece? That and then this piece. The true weight loss, 12 months, Atkins diet. That is our parameter. That's the thing we're interested in learning about, right? And you can find that in the problem right here. And then remember, we say is between, and then this last piece, we just apply our confidence interval to the problem. Negative 3.64 means we've lost 3.64 pounds. Negative 0.56 means we've lost 0.56 pounds, about half a pound. Okay, so again, we are 95% confident that the average weight loss in 12 months on the Atkins diet is between 3.64 pounds and 0.56 pounds. Is this an effective diet? What does it mean for the diet to be effective? an effective diet means that you're expecting to lose weight. So if that's your definition, and you might have an issue with this, which we'll talk about in a second, if your definition is just, okay, it's effective if we lost weight, then this would be an effective diet in your opinion, because based on this confidence interval, we believe the average weight loss for somebody on this diet is them losing weight. So how can I say that? Let's copy this confidence interval down here, right? So how can I say that that's what's going on? Like, why does this tell me they lose weight? Well, what if they didn't lose weight? If you didn't lose weight, what would your average weight loss look like? So no weight loss, what would that look like? That would look like your average weight loss is 0 pounds. Okay, but here's the thing. Is 0 pounds lost a plausible value? Is that in our set of plausible values? No, 0 is not in our plausible values, because these are all of the plausible values that we believe based on our confidence interval. So 0 is not plausible, which means if you tell me that you believe 0 pounds is the average weight loss, I would test that using simulation theory, whatever, and I would tell you I reject that hypothesis. I'm not saying that I'm 100% certain it's wrong. I'm just saying based on our statistics, I would reject that that's true. Based on this confidence interval, I am confident that people are losing weight on average. Okay, so here is the real question then. Is this an effective diet? Well, this is where you have to start thinking about what effective means to you. So you are somewhere on average, we think, you're somewhere on average going to lose between 3.64 pounds and 0.56 pounds. That is the average weight loss we believe on this diet. Okay, so that's telling us that on average people are losing weight on the diet. But this plausible value confidence interval is saying we think that the true average is somewhere in here. Anywhere in here. I don't have any reason to believe it's one place or another. I'm just saying it's plausible that it's somewhere in here. So we could have it that the true parameter is 0.56 pounds lost. Or it could be 1 pound lost. Or it could be 2 pounds lost. So what you have to be thinking is that effective to you? Are you happy signing up for this diet knowing that the average weight loss in a year is somewhere between 0.5 pound and 3.5 pounds? Is that good enough for you? So this answer is it depends. Because we really do believe, 95% confident, that somewhere in this confidence interval is the true average weight loss for a person on this diet. But that's over 12 months. We think that on average you're going to lose somewhere in here, this many pounds, somewhere about 3.5 to 0.5 pound. And so it depends. It's up to you. If you wanted to lose weight and you were comparing diets and you found this diet and saw this statistic, it's possible you might say, okay, I think maybe this is going to help me lose weight, but it doesn't seem like it's going to help me lose much, and so this is not what I'm looking for. And so you have to be able to take the statistics, right? The statistic answer is, yep, this is effective. I have statistically significant evidence that the average weight loss is going to be some amount of weight. So I'm fairly confident that on average people are going to lose weight on this. That's just what the statistic says. But you have to be able to kind of take that and understand what it's saying and apply your own extra factors to this. You have to be able to say, well, okay, that's great. Somewhere we think on average between 3.5 to 0.5 pound, but that's not quite enough for me to pay for this diet or to drastically change the way I'm eating for this diet or whatever you'd have to do to be on this diet. So that's the extra piece that you have to be able to bring to the table in order to do statistical analysis and have it be useful. So it's not just the stats. You've got to also bring that real world experience into it and make sure that you understand that just because it's statistically significant does not mean that it's real life significant for you. So very important point there. Statistical significance does not necessarily mean real life significance for making decisions for you. So always keep that in the back of your mind. You hear statistically significant? Awesome. You hear that I'm telling you 95% confident the average weight you will lose weight on this. Awesome. Your next question should always be, okay, how much? What's the actual confidence interval? How much weight do you think I'm going to lose? Because if it's plausible I could only lose half a pound, maybe I'm not, running to try to sign up to this diet. So in example 6, we are going to do something similar to example 5, where we're taking some extra piece of information and applying our confidence interval to try to answer a question. So back in example 4, we had these confidence intervals. All right. So remember, example 4 was all about what's the proportion of U.S. adults who drink alcoholic beverages. And so we had these intervals. So the extra piece of information is, okay, your friend claims that 70% of adult Americans consume alcoholic beverages. Based on your confidence intervals, what do you think about that? And so whenever this type of problem comes up, what you're doing is you're saying, so if someone claims a value for the parameter and you've got a confidence interval, your main question is the claim plausible? Just to put it into our words for stats. We're asking, okay, my friend said 70%. Am I saying, okay, that's plausible? Or am I saying, you know what, I've got evidence that that's not true? So what info do we have? Well, we could go to the applet, type in pi as 0.7, run a simulation, use the theory if we wanted to, and see the p-value. But we've done that work already. Look at these confidence intervals. Remember, the confidence interval is describing to you which values for the parameter, pi in this case, are plausible. So all you have to do is take 0.7. So remember, 70% is 0.7. Take this, go look at your confidence interval. Is 0.7 in this confidence interval? No, it's too big. So because 0.7 is not in here, we would reject this as a plausible value. So this is not plausible. So we'll keep going. Check in here. Is it in this one? Nope. Is it in this one? Nope. So it is not a plausible value for any of our confidence intervals. So we are feeling pretty sure, again, never 100%, but we're feeling pretty sure that 0.7 is not a plausible value. We reject that. All right? So all we have to do, if somebody claims a value at us and I've got a confidence interval here, I don't have to test this as my pi and go through all the unit 1 stuff. I've already done that. Look at the confidence intervals. If their claim is inside, then we're going to say, okay, you're plausible. If their claim is not inside, like in this example, we're going to say, nope, I don't think so. Again, not 100%, but based on our information, we don't believe that this is plausible.